Hello, everybody. Today we'll talk about tolerance curves. So, it is often necessary to monitor the acoustic behavior of a product. Manufacturers set the threshold the product must meet, failing which it is termed as not acceptable. In order to evaluate the acoustic performance of a product, we use tolerance curves, and these curves help to assess whether a product is within the limit or is violating the limit. So there are different types of tolerance curves. The curves with respect to time, with respect to frequency, and with respect to minimum and maximum ranges. Let's check each one of those. So the first is a time-based curve. So in this case, we have the x-axis as a time axis and the y-axis is sound pressure level. Now the y-axis can be literally anything what you want to monitor. In this case, I want to monitor sound pressure level, hence the y-axis is SPL. Now the time axis in this case, I've used 10 seconds, but it can be as long as you want. So in this case, we have a red line exactly at 70 decibel. So it means that we have set a hard limit at 70 decibel. So when we are going to measure a noise from a product, we need to ensure that its sound pressure level that it emits, does not exceed 70 decibel over the course of time. So this is what a time-based tolerance curve does. So we see the example. So we have this curve again, but then we have measured a sound pressure level of a product and we plot it over here and we see that the blue curve, constantly goes up and down over the tolerance curve. So in this case, it's clearly a failure because it's exceeding the hard limit that we set of 70 decibel. Of course, there are certain time zones where it's below the curve, but then it doesn't make sense because it has already exceeded, so it's a failure. So if in case the measure signal was like hovering around 60 decibel, then it's a pass case because it's not exceeding the hard limit that we set, which is at 70 decibel. The next is a frequency-based curve. In this case, the y-axis is still the same, which is sound pressure level, but the x-axis is no longer the time axis, but rather the frequency axis. Now, the frequency range is from 20 to 20 kilohertz because that is the audible range or the range at which humans can hear sounds. And the curves, as you can see, are like in a trapezoidal format. This is because of our human hearing. Our human hearing is very good in the mid frequencies, but poor at lower and higher frequencies. So the same concept applies here. So we measure a signal, we measure the sound emitted by a product, and perform the FFT and plot the spectrum, FFT spectrum, over this tolerance curve. So I've measured a signal, I've plotted this in the blue color. So as you can see here, the spectrum from 20 to 20 kilohertz is well below the hard limit of the tolerance curve. So in this case, it's a pass case, it's not fail because any of those spectrum are not exceeding the limit that we set. So this is a good case. The next is a range-based curve. So in case if you're designing product sound quality and if you want the spectrum to be within a particular range, upper and lower limit, you can employ this curve and check if the spectrogram is within this limit. You can also, in this case, the x-axis is frequency, but it can also be time, and you can have more lenient limit where you don't have one hard limit of a particular sound pressure level, but rather an upper and lower limit, and ensure that the sound pressure level is between those limits. So next is an interesting case. It's a borderline situation. What if the measured sound pressure level is very close to this tolerance curve that we have set? In case of level versus time or a time-based tolerance curve, the measured signal is pretty close to the tolerance curve, but it's not touching it nor exceeding it. It's just close. There is a very small gap between the curve and the tolerance curve. And the same on the frequency-based tolerance curve. As you can see here, the signal is in purple and it's pretty close to the tolerance curve, but it's not touching it. So what would you do in this case? Well, theoretically, in this case, it's a pass because it's not exceeding, neither is touching. But then if you think over it, you need to repeat the measurement. Finally, we're not trying to just do a pass-fail analysis here, but we're rather checking if the product is performing, is meeting the standards. So repeat the measurement again and check if this is a situation. There's a good chance that it's going to exceed or touch the curve. So, for example, if there's like 0.1 decibel below the curve, and if you repeat the measurement, there's a good chance that it's going to exceed that. So in that case, it will become a failure. So better to repeat the measurement and check if this is really the situation or not. So to conclude, tolerance curve help to assess whether a product is within the limit or is violating the limit. So we're not just using time-based tolerance curves, but we're also using frequency-based so as to check if certain frequency spectrum are violating the limit, which is not possible to capture in a time-based tolerance curve because we don't have any information about frequency. So that's good. And if the measure signal is in the borderline, repeat the measurements to verify. All right. Thank you for watching this video. I hope you enjoyed it. Have a great day.